I will show you how to conduct the analysis of the data you have collected in order to determine the mass of the contraption, namely the iOLab device housed inside the duct tape roll. So we have collected here data for both the acceleration about the three axes, namely the x, y, and z axes, as well as the force in the y direction measured by the force sensor. So the first thing to note is that the data for the acceleration in the x and the z directions are immaterial. They are consistent with 0, so we can remove those. The data about the y-axis is the one which is consistent with the acceleration due to gravity. So we can measure what the average acceleration due to gravity is at the location where we do our experiment by selecting some large portion of this data. So in order to do the selection, remember you have to make sure you click on the analysis tool up here. Okay, so I've selected a reasonably large portion of the data, so I can see here that when I do so, I get the average value for the acceleration due to gravity, and it turns out to be consistent with 9.8 meters per second squared. You can see here it is negative 9.799 meters per second squared, and the negative sign is of paramount importance, and I will leave that for you to figure out why that is so. Over that same range, if you look at the force data, remember I said that in the earlier video it flatlines, and the flatlining of the force sensor data is consistent with 0. However, when you select that large range, you notice here that the average force that is read by the force sensor is 0.126 newtons. So this is because you have actually inserted the little eye bolt into the force sensor. So there's that eye bolt that you inserted in there has a tiny amount of mass. So that compresses upon the spring a little bit, and that produces a residual reading of 0.126 newtons. Another thing that happens is because you have screwed it in there, there's a little bit of torsion that exists as well, so the spring is in a little bit of tension because of that. As a result of this, there is a residual 0 reading, and this is of paramount importance. Because when you lift up the device, the reading changes to the value down here, and the change in the reading is from this original residual value of 0.126 newtons. So please make a note of this 0.126 newtons, and also remember that it comes here with a plus sign, so that is also of paramount importance. Next thing what we're going to do is we're going to measure the average reading of the force sensor during the time interval when you had lifted the contraption in the air and held it steady. So I'm going to select some portion of the data here, being careful to rule out the very edges. So I'm selecting data well within this period of time when you held it up in the air in a stable position. And notice here that when I select that portion of the data, I get an average reading for the force read by the force sensor, and that is negative 3.864 newtons. So the change is this final value, which is minus 3.864 newtons, minus the initial value, which is 0.126 newtons. Right? So that is the change in the reading of the force sensor, so which means that the change in the reading that you get is essentially the applied force which you applied to the force sensor to keep the entire contraption steady in the air. Now you applied a force which is exactly equal to the force of gravity. As a result, the change in force that you calculate, the change in the reading from this reading here to this reading here, the change, the final value minus the initial value, bearing in mind the signs of those values, gives you the force due to gravity which is acting on the contraption. Now you've already seen that in this portion of the data when you selected for the acceleration, you found out that the acceleration was negative 9.8-ish meters per second squared. So you can take the change in the force, bearing in mind the sign, divide it by the acceleration, bearing in mind the sign, and that should give you the mass of the contraption.